This is section 2 of chapter 12, probability, independent and dependent events. Let's start by defining independent events as two events where the occurrence of one does not affect the occurrence of the other event. Let's pretend that Sally has a coin in her hand and she flips it. Also pretend that Jack has a die in front of him and he rolls it. Is it possible that Sally will flip tails and that Jack will roll a 3? Yes, this is possible because the side that Sally flips on her coin has no bearing on the number that Jack rolls on his die, and vice versa, although the combination may be unlikely. Similarly, if I told you that Sally was going to flip tails, would that make it more likely that Jack will roll a 3? No, because the occurrence of either event does not affect the occurrence of the other, which is the definition of independent events. Let's say I have a bag full of marbles. I have 4 red, 3 blue, and 2 green marbles. Suppose I shake up the bag and you pick out a marble. You look at it, then put it back. I shake up the bag and you pick again. Again you look at it and put it back. One last time, I shake the bag and you pick for a third time. What is the probability that all 3 marbles were red? So first off, we know that these events are independent because each time you pick out a marble, you end up putting it back, so it does not affect the sample size of the marble. We can calculate the probability of independent events by using this equation, and states that two events, A and B, are independent events if and only if the probability that both events occur is the product of the probabilities of the events. So what is the probability that the first marble will be red? We know that the sample is 9 marbles because it mentioned in the problem that there are 4 red, 3 blue, and 2 green marbles. Of those 9, there are 4 red, which means that the probability that the first marble will be red is 4/9. Since we put the first marble back before you make the next selection, the probability that the second marble will be red is again 4/9, and similarly for the third marble. So using the equation, we multiply the 3 probabilities together, which are all the same, 4/9, to get 9%. So example 1. A bag contains 6 pieces of paper numbered 1 through 6. A student randomly selects a piece of paper, replaces it, and randomly selects another piece of paper. Use a sample space to determine whether randomly selecting a 5 first and randomly selecting an odd number second are independent events. So you want to select a 5 first, out of a bag containing 6 pieces, each with a number 1 through 6. Since there is only one 5 out of 6 possible options, the probability of picking a 5 is 1/6. Then you want to randomly select an odd number after replacing the first. Since you replace the first, the sample space is still 6, and there are 3 odd numbers, 1, 3, and 5, to pick out of the bag. So the probability of picking an odd number are 3/6. These two together, you get 1/12, which is the total probability that both of these events will occur. So answering the question, these events are independent events because you replace the piece of paper, so the probability of picking any of the numbers 1 through 6 is the same for each time you pick. Example 2. A bag contains 6 pieces of paper numbered 1 through 6. A student randomly selects a piece of paper, does not replace it, and randomly selects another piece of paper. Use a sample space to determine whether randomly selecting an even number first and randomly selecting a 4 second are independent events. Going off our definition of independent events, where one event's occurrence does not affect the other event's occurrence, you can tell that these two events are not independent because you do not replace the piece of paper after you pick it. So for the first one, you have a sample space of 6, and for the second one, you have a sample space of 5 because you only have 5 left after picking the first one. So these cannot be independent events. Example 3. A card is drawn from a deck and replaced. Then a second card is drawn. Find the probability of getting a queen and then an ace. So because these cards are replaced, you know that these are independent events, and you can multiply the probability of the events together to get the total probability of the events occurring. So find the probability of getting a queen. So there are 4 queens in a deck and 52 cards in a deck. So the probability of picking a queen is 1/13. And then an ace. There are 4 aces in a deck, which also has 52 cards. So you multiply 1/13 by 1/13 to get a total probability of 1/169. So referring back to the top of the page, what happens if we don't put the marbles back after each pick? Let's pretend that you first pick a red marble. If we don't put the marble back, does that change the likelihood of the next pick being red? Yes, because there would be one less red to choose from in the bag. In this case, the events are dependent events. Let's define dependent events as two events where the occurrence of one does not affect the other. Conditional probability is the probability that event B occurs given that event A has occurred. So example 4. The probability that Sam parks in a no parking zone and gets a parking ticket is 0.06, and the probability that Sam cannot find a legal parking space and has to park in the no parking zone is 0.2. On Tuesday, Sam arrives at school and has to park in the no parking zone. Find the probability that he will get a parking ticket. So here is a grid that represents the parking lot. The green are the spaces where Sam can park legally, and this right here, these two rows, are the no parking zone. There are 6 spots out of the total 100 spots, so 0.06 or 6% of spots where he can get a parking ticket. The rest is just the no parking zone, so 20 spots or 0.2 of the sample. So on Tuesday he arrives and has to park in a no parking zone. What is the probability that he will get a parking ticket? So out of the no parking zone, 0.06 out of 0.2 is the chance he'll get ticketed. So 0.3 is the chance that he will park in the no parking zone and get a parking ticket. A recent survey asked 100 people if they thought women in the armed forces should be permitted to participate in combat. The results of the survey are shown. Find the probability that the respondent answered yes, given that the respondent was a female. So we know conditional probability is the probability of A and B over the probability of A. And the probability of A will be the probability that the respondent was a female, and event B will be that the respondent answered yes, and then so we divide again by the probability that the respondent was a female. So when we look at our chart that's provided, the probability that the respondent answered yes, which is this column, given that the respondent was a female, is this. So of the people who are females, there are 50 total, and the females that answered yes, there are 8. So the probability that the respondent answered yes, given that the respondent was a female, is 16%. And for part B, it's very similar. Find the probability that the respondent was a male, given that the respondent answered no. So the number of respondents that answered no was 60. And the number of male respondents that answered no was 18. So 30% is our final probability. So example 6, state which events are independent and which are dependent. A, tossing a coin and drawing a card from a deck. These events are independent because neither one has a bearing on the outcome of the other. B, drawing a ball from an urn, not replacing it, and then drawing a second ball. These events are dependent events because one ball is not replaced and then the second ball is drawn, making the sample size smaller and therefore them dependent events. C, getting a raise in salary and purchasing a new car. These are dependent events because someone might not have bought the new car had they not got the raise in salary. D, driving on ice and having an accident. These are dependent events because the accident could be as a result of driving on the ice. E, having a large shoe size and having a high IQ. These events are independent because there is no way that they are in any way correlated. F, a father being left-handed and a daughter being left-handed. These events are dependent because genetics and the traits that are carried down would result in the daughter being more favored left. G, smoking excessively and having lung cancer. These events are dependent events because lung cancer is known to result from smoking excessively. H, having an excessive amount of ice cream and smoking an excessive amount of cigarettes. These are independent events because one might not lead to the other. Use a spinner to find the probability that you get an even number on your first spin and a number less than 3 on your second spin. These events are independent events because the spinner does not change in between spins. So the probability of getting an even number on your first spin, there are 4 even numbers, so 4 out of 8. And then a number less than 3, there are only 2 numbers less than 3, so 2 out of 8. When you multiply those together, you get 12.5% as the probability that you get an even number on your first spin and a number less than 3 on your second spin. 9 women and 6 men are on a committee. 2 people are randomly chosen from the committee members to serve as chairperson and treasurer. Find the probability that both events A and B occur. A, the chairperson is a man. B, the treasurer is a woman. So of the 9 women and the 6 men, that makes 15 total people. So 9/5 of the committee are women, and 6/15 are men. The chairperson is picked first, so you want it to be a man. So the probability of picking a man out of 15 people is 6/15. Then you have 1 less person to pick from who can be the treasurer, and you want it to be a woman, so there are 14 people left, and of those there are 9 women. So 9/35, or 25.7%. Let's say again I have 4 red, 3 blue, and 2 green marbles in a bag. If 2 marbles are randomly selected from the bag without replacement, what is the probability that both will be red? So assume the first marble was red. What is the probability that the next one will also be red? Since there are 8 marbles left in the bag and 3 of them are red, the probability of the second one being red is 3/8. So using the formula for dependent events, we get 17%. A bag contains 10 red marbles and 5 blue marbles. You randomly select 3 marbles from the bag. What is the probability that all 3 marbles are blue when you A, replace each marble before selecting the next one, and B, you do not replace each marble before selecting the next one? Compare the probabilities. So for part A, you replace each marble. So out of the 15 marbles total, and you want to pick a blue marble, there are 5/15 blue marbles in the bag, and since they're independent events because of replacement, you multiply that by 5/15 for the second pick and 5/15 for the third pick to get 4%. For part B, when you do not replace the marble before selecting the next one, you have 5/15 of the marbles initially are blue times 4/14 of the marbles after the first pick are blue, because you lose 1 blue marble and then you lose 1 total marble. Similarly, for the third pick, you have 3/13 blue marbles, which is 2%. So the percentage halves. A quality control inspector checks for defective parts. The table shows the results of the inspector's work. Find the probability that a defective part passes. So of the defective ones, there are 29, and 5 of them pass. So 5 out of 29 is 17.2%. Find the probability that a non-defective part passes. Of the non-defective parts, there are 217, and 208 of those pass. So 208 divided by 217 is about 95.9% after multiplying by 100. Example 12. At a clothing store, 75% of the customers buy pants. Only 20% of the customers buy pants and a belt. What is the probability that a customer who buys pants also buys a belt? So you want to find what percentage of the 75% of customers buy pants and a belt. So 20% of those who buy pants, so 20% of the 75% buy pants and a belt. So 26.6%. A coin is flipped and a die is rolled. Find the probability of getting a head on the coin and a 4 on the die. So you want to get a head on the coin, and there's a 50% chance that you will flip a head. And a 4 on the die, there are 6 options on a die, so 1/6. So there is a 1/12 probability that you will do both. A Harris poll found that 46% of Americans say they suffer great stress at least once a week. If 3 people are selected at random, find the probability that all 3 will say that they suffer great stress at least once a week. So these are independent events. So 46 out of 100 Americans say they suffer great stress. So that's the probability that the first person will suffer great stress. Similarly, 46 out of 100 is the probability that the second and third person will suffer great stress at least once a week. So 9.7%. This problem is very similar. Approximately 9% of men have a type of color blindness that prevents them from distinguishing between red and green. If 3 men are selected at random, find the probability that all of them will have this type of red-green color blindness. So 9 out of 100 men suffer from this type of color blindness. So this is the probability that the first man will suffer color blindness. Similarly, 9 out of 100 is the probability that each of the next men will suffer. So 0.073%. At a university in western Pennsylvania, there were 5 burglaries reported in 2003, 16 in 2004, and 32 in 2005. If the researcher wishes to select at random 2 burglaries to further investigate, find the probability that both will have occurred in 2004. So in total, there were 53 burglaries, and 16 occurred in 2004. After this, there are 52 burglaries after the first one is selected, and 15 burglaries left in 2004. So 60 over 689 is about 8.7%. The Neckwear Association of America reported that 3% of ties sold in the United States are bow ties. If 4 customers who purchased a tie are randomly selected, find the probability that at least 1 purchased a bow tie. So 4 customers times 3 out of 100, or 3%, is about 12% who purchased at 1 bow tie. So 3 cards are drawn from an ordinary deck and not replaced. Find the probability of these 3 events: getting 3 jacks, getting an ace, a king, and a queen in order, getting a club, a spade, and a heart in order, or getting 3 clubs. So there are 52 cards in a deck, and there are 4 jacks. So the probability of picking 3 jacks for the first one is 4 out of 52, and then you remove 1 jack and 1 card from the overall deck, so 3 out of 51 is the probability of picking a second jack, and then 2 out of 50 is the probability of picking a third jack. Which gives a percentage of about 0.018%. Getting an ace, a king, and a queen in order, there are 4 aces and 4 kings and 4 queens, but each time you remove a card. So 4 over 52 times 4 over 51 times 4 over 50. Because there are 4 of each, but then for the second pick, you only have 51 cards to choose from, and for the third pick, you only have 50 cards to choose from. So that is 0.048%. Similarly, getting a club, a spade, and a heart in order, there are 13 cards of each suit, so 13 out of 52 is the probability of picking a club, then 13 out of 51 because you remove 1 card from the deck, then 13 out of 50 because you remove 2 cards by that point. So that has a percentage of 1.66%. And then getting 3 clubs is similar to getting 3 jacks, except there are 13 clubs. So 1352 times 1251 times 1150. So 1.29%. So a person selects 3 cards from an ordinary deck and replaces each card after it is drawn. Find the probability that the person will get at least 1 heart. So there are 13 hearts out of 52 cards. So the probability of picking a heart on the first one is 1352. And then for the second one, because it is replaced, is also 13 out of 52, and so is the third. So when you multiply those out, you get a probability of 1.56%, which is similar to the picking 3 clubs on the previous page. 2 red balls and 1 blue ball. Box 2 contains 3 blue balls and 1 red ball. A coin is tossed. If it falls heads up, box 1 is selected and a ball is drawn. If it falls tails up, box 2 is selected and a ball is drawn. Find the probability of selecting a red ball. So there is a 50-50% chance of picking heads or tails on the coin. And in box 1, which would be if heads is selected, there is a 2/3 chance of picking a red ball. If tails is the flip of the coin, then it goes to box 2, which has a 1/4 chance of picking a red ball. So since there is a 50% chance of picking heads, you multiply that by 2/3 to get a 1/3 chance of picking a red ball from box 1. Similarly, for box 2, 1/2 times 1/4 is a 1/8 chance of picking a red ball from box 2. Add these together and get 11/24 as the probability of selecting a red ball.